Welcome to the Deep Dive, where we unpack the most interesting and impactful research.
Great to be here.
So today, we're tackling a really fascinating new paper. It looks at how reinforcement learning, AI that learns by doing, can optimize this fundamental problem of searching.
Right.
Specifically, when the smartest move might actually be to, give up and start over.
With a reset.
Exactly. And we'll explore how these AI agents learn these reset strategies and sometimes even find ways that are better than our existing best approaches, which is pretty cool.
Yeah, get this. It's not just about finding things faster. Sometimes it's about finding smarter ways to search.
That's the core idea.
Mm-hmm.
Think about it efficiently finding a target. It could be anything, right? A protein for a biologist, the best setting for a machine learning model.
Or just your keys when you're late.
Exactly. It's a universal challenge.
Yeah.
And this paper really digs into how AI can learn the optimal timing for hitting that reset button.
Which feels counterintuitive, but it can seriously improve search efficiency in a lot of situations.
Totally. Okay, so this isn't just like random trial and error. This research uses reinforcement learning quite deliberately to teach agents when and how to reset their search strategically in different kinds of environments.
And the exciting part, as you said, is they weren't just trying to get the AI to copy what we already knew.
Right.
The key insight here, I think, is that by setting up the search problem as this reinforcement learning task, the AI agents could sort of develop their own intuition about searching. They not only rediscovered known efficient methods, which is a good sanity check, but in some really interesting cases, they came up with completely new ways to search. And these ways actually outperformed the established benchmarks.
It's like watching AI discover new scientific strategies almost.
Yeah, it kind of is.
So in this deep dive, we're going to break down the paper's main approach, how they set up the problem, how they train these agents. Then we'll look at their key findings, what happened in simple searches versus more complex ones.
And then the fun part, brainstorming a bit.
Exactly. We'll put on our thinking caps and explore some of the future research directions this work might open up.
Sounds like a plan. So maybe before we get into the nitty-gritty, let's just frame why this kind of research matters.
Good idea.
Target search problems, they're just everywhere. Biology, computer science, optimization.
Economics, robotics.
You name it. And in so many of these cases, getting stuck is a real issue. Searching in an area that's just not productive.
Right, and that's where resetting comes in. It's like, stop banging your head against the wall.
Exactly. Whether it's an optimization algorithm stuck in a local minimum or, some kind of random search process that just needs a fresh start, resetting to a known point can really speed things up.
We've known this for a while in simple cases, right? Like for basic random walks, simple Brownian motion, resetting at regular intervals is often provably the best way.
That's true for the simple models.
Yeah.
But what's fascinating is as soon as things get a bit more complicated.
Which they always do in the real world.
Right. Real search spaces are messy, and the agents doing the searching might have memory, or they can move in specific ways, not just randomly. And all these extra layers of complexity, they make it incredibly hard, maybe impossible, to just sit down and mathematically figure out the absolute best time to reset.
Okay, so that's the gap this paper is trying to fill. Instead of deriving the perfect mathematical formula, which might not even exist for complex cases.
They turned to machine learning, specifically reinforcement learning.
Which makes sense, right? The agent learns by trying things out.
Exactly. It's trial and error, but guided. Every move, a step, or a reset is an action. Finding the target is the reward.
And over time, the agent learns a policy, like a set of rules.
Yep, a policy that tells it what action is best in any given state to maximize its chances of getting that reward, finding the target efficiently.
And the researchers suggest this isn't just about making search faster, practically speaking.
No, there's a deeper potential benefit. By watching how these AI agents learn and what strategies they come up with, we might actually get new insights into the fundamental principles of searching itself.
Like using AI as a microscope for exploring search strategies.
That's a great way to put it. Probing how to find things in complex systems.
Okay, let's get into the methodology then. How did they actually build these AI searchers? What was the setup?
So they framed the search problem using something called a Markov decision process, an NDP.
Right, standard in RL.
Yeah, think of it like a game. The agent is in a certain state, may be defined by how long it's been searching since the last reset.
Okay.
From that state, it picks an action, move, reset, whatever. That action leads to a new state. And the whole goal is to learn a policy, a way of choosing actions that gets the most reward in the long run.
And the reward here is just finding the target.
Finding the target, exactly.
The paper looked at two main types of agents, right? The reset agent and the turn reset agent. Let's start simply with the reset agent.
Okay, the reset agent was pretty basic. Its actions were essentially take a random step, like Brownian motion.
Like a dust particle jittering around.
Pretty much, yeah. Diffuse randomly. Or, action number 2, instantly reset back to the starting point.
And its state was just how many steps it had taken.
Just the number of steps since the last reset. Simple. Reward only when it hit the target.
Okay, simple, but captures the core reset idea.
Yeah.
What about the turn reset agent? Sounds more capable.
It had more options. It could still reset to the origin, that's crucial. But it could also choose to just continue moving in its current direction with a fixed step size.
Okay, persistence.
Or it could pick a new random direction and then take a step.
Got it. So reset, continue, or turn.
Right. And because it could turn, its state needed to be a bit richer. It included both steps since the last reset and steps since the last turn.
Makes sense. More complex behavior needs more state information. Reward was still finding the target area.
Yep. Entering the target area triggered the reward.
So these agents are exploring, trying to find the target, and they have this reset option. How did they actually learn the best time to use it? What was the RL algorithm?
They used an algorithm called projective simulation, or PS.
Oh?
It's known to be pretty good in situations where the reward is sparse, which is common in search problems, right? You might search for a long time before you actually find anything.
Yeah, the reward signal is weak.
Exactly. So PS works by essentially propagating the reward signal backward in time. When the agent finally gets a reward, PS strengthens the connections for the whole sequence of state action pairs that led to that success.
Ah, okay. So it helps figure out which earlier decisions were actually useful, even if the reward came much later.
Precisely. It's like learning from the successful paths, figuring out those crucial early steps.
Like figuring out the breadcrumbs that led to the treasure.
That's a good analogy, yeah.
And they started these agents off completely naive, right? An unbiased policy.
That's right. Initially, all actions were equally likely. The idea was for the agent to figure out effective searching completely on its own, through learning.
And how did they know if the learned strategies were any good? Did they compare them to something?
They did. They set up some baseline strategies for comparison. For the simpler reset agent, the main baseline was what they called sharp periodic resetting.
Meaning reset at exact regular intervals.
Exactly. Which, as we mentioned, is known to be optimal in some simple theoretical cases. They also compared against a constant probability of resetting over time.
Okay. And for the turn reset agent, the baseline was more complex too.
Yeah, for that one, they designed a baseline that involved walking straight for a fixed time, making a sharp turn, continuing straight again, and then resetting after another fixed time.
And they optimized these baselines.
Yep. They found the best parameters for these sharp strategies, often numerically, to make sure it was a fair fight against the learned agents.
All right, setup complete. Let's get to the results. What did the AI agents actually learn? Starting with the reset agents in 1D and 2D.
Well, the results were pretty compelling. The RL agents, they successfully learned resetting strategies that were very close to optimal in both 1D and 2D Brownian search.
Close to that theoretical sharp resetting baseline.
Very close in terms of efficiency, yeah. And significantly better than just resetting with a constant random chance.
So basically, the AI rediscovered a known optimal strategy without being told.
Pretty much. Which is a really strong validation of the whole reinforcement learning approach here.
That is impressive. What did the learned policies actually look like? How did the probability of resetting change over time?
It showed this really interesting pattern. Right after a reset, for the first few steps, the agent learned to have a low probability of resetting again.
Okay, don't reset immediately. Makes sense.
Right. But then, after a certain number of steps, the probability of resetting would shoot up quite sharply.
Ah, so it learned a sort of threshold.
Kind of, yeah. And critically, when that probability jumped up scaled with the target distance, if the target was further away, the agent would search longer before this jump occurred.
So it learned to be more patient if the goal was likely further out. That's quite intuitive.
It is. And they also looked at the distribution of the actual times when the agent did reset. And that distribution showed a clear peak right around the theoretical optimal reset time for the sharp strategy.
So it really honed in on the best timing.
It did. Although there was one slightly weird thing they noticed initially.
Oh?
The agents tended to have a surprisingly high probability of resetting very early on, like in the first 1 or 2 steps right after a reset, which seems suboptimal.
Yeah, why reset almost immediately? Any idea why that happened?
The authors thought it was probably an artifact of the sparse reward. Because finding the target was so rare, the agent maybe didn't get enough feedback to properly learn that resetting immediately after a reset wasn't helpful. It's hard to learn the fine details when success is infrequent.
That makes sense. If you rarely succeed, it's hard to punish those tiny initial mistakes.
Yeah.
So did they do anything about that?
They did. They tried what they called expert-guided policies. Based on the intuition that resetting immediately is bad, they manually forced the reset probability to be 0 for the first few steps.
So they gave the AI a little nudge based on human understanding.
Exactly, just a small tweak. And that actually improved the efficiency further and made the average reset time even closer to the theoretical optimum.
Interesting. It shows how combining machine learning with a bit of domain knowledge can really pay off.
Definitely. It's not always about pure black box learning. Sometimes a little guidance helps.
Fascinating.
Yeah.
So the AI gets you like 95% of the way there, and human intuition polishes it off. Okay, now for the really exciting part, the turn reset agents, the more complex ones in 2D. What happened there?
Yeah, this is where it got particularly cool. Remember, the baseline for this agent was that sharp strategy. Go straight, turn sharply, go straight again, then reset at fixed times.
Right, optimized based on theory.
Optimized, yeah. But the RL agents in this more complex setup learned strategies that, for some target distances, actually beat that baseline.
Whoa, hold on. The learned strategy outperformed the engineered, theoretically inspired baseline.
In certain regimes, yes. The AI didn't just match it, it found something better.
Okay, that's significant.
Yeah.
So it wasn't just mimicking, it was genuinely innovating, finding a superior approach in some cases. What did these better strategies look like?
Well, the learned policies still had structure. They generally started by moving straight for a while. Then the probability of turning would start to increase, and eventually the agent would reset. The initial straight line distance it learned was actually pretty similar to the baseline, roughly matching the target distance.
Okay, so far, similar. But the reset part must have been different if it was doing better.
That was the key difference. Instead of resetting around the time suggested by the analytical baseline, the learned strategies did something else. After that initial reach phase, they involved taking a few shorter steps, sort of exploring locally.
Like searching around the expected target area.
Exactly. A bit more local exploration before finally resetting, often at a later time, maybe around twice the target distance compared to the baseline reset time.
So the AI figured out, get close, then do a more careful local search before giving up and doing a full reset.
That seems to be the strategy it discovered, a kind of 2-phase approach, long reach, then local refinement. And this seemed to be more effective, especially as the paper notes, around target distances where the optimal sharp baseline strategy itself had to change its rules.
Right, so maybe where the simple sharp rule was less robust, the learned strategy was more adaptable.
That's a good way to think about it. The RL agent found a more nuanced approach that worked better, particularly in those transition zones. It really shows the power of RL to find non-obvious solutions when the problem gets complex.
Okay, this is really cool stuff. So let's try and summarize the main takeaways from this research. What should we remember?
Well, first, I think it's a strong confirmation that reinforcement learning is a really powerful tool for finding efficient resetting strategies. That's clear. Second, it shows these agents can, recover known optimal strategies on their own, which builds confidence.
Right, they learned the sharp resetting thing without being told.
Exactly. But maybe the most exciting takeaway is that in more complex cases, RL can actually uncover new, interpretable strategies that outperform the ones we came up with.
Finding genuinely novel solutions.
Yep. And fourth, that synergy between learning and expert knowledge, like manually setting the initial reset probability to 0, can be really valuable for fine-tuning.
And critically, these learned strategies weren't just black boxes, right? They were interpretable.
Largely, yes. We could look at the policies and understand why they were doing what they were doing, like the low initial reset probability, the scaling with distance, the local search phase. That interpretability is huge.
Absolutely. It's not just getting a better number, it's gaining understanding about efficient search itself. Which brings us perfectly to our novel notions segment. Based on this work, what kind of future research ideas spring to mind?
Okay, so one idea that feels like a natural extension is adaptive resetting based on environmental feedback.
So not just resetting based on time or steps.
Exactly. In the paper, the state was mainly about step since reset or turn. But imagine an agent that could actually sense things about its local environment.
Like what?
Well, in a physical search, maybe it's terrain difficulty or a faint scent trail. In optimization, maybe it's like the local gradient of the function is trying to minimize. Is it flat? Is it steep?
Okay, I see. So the agent's decision to reset wouldn't just be clock watching. It would depend on whether the current path feels promising or not.
Precisely. If an optimization algorithm finds itself in a really flat, boring region of the lost landscape, maybe it learns to increase its reset probability. Nothing happening here, let's try somewhere else.
Or a foraging robot, if it hasn't detected any scent for ages, maybe it resets its search pattern more often.
You got it. This builds on the paper's success, but adds this layer of real-time context. Most current work is time or step-based. Adding environmental cues feels like a big step towards truly smart adaptive search, especially in really complex or dynamic situations where a fixed reset schedule just won't cut it.
That feels really powerful, letting the strategy adapt on the fly based on actual progress. Okay, what's another potential direction?
Another one that seems promising is thinking about hierarchical resetting strategy.
Hierarchical, like multiple levels of resetting.
Sort of, yeah. Think about searching in a really large space that has some kind of structure.
Yeah.
Like exploring different neighborhoods in a city first, level 1, and then deciding which streets to search within a chosen neighborhood, level 2. An agent could learn policies for resetting at different levels. When should I give up on this whole neighborhood and try a different one? That's a high-level reset. And then within a neighborhood, when should I stop walking down this street and backtrack or try another one? That's a lower-level reset.
Ah, I see. So you break down the big search into nested searches, each with its own potential reset logic.
Exactly. It connects nicely to ideas in hierarchical reinforcement learning, tackling big problems by breaking them into sub-problems.
Mm-hmm.
Animals might do this, right? Broad exploration, then focus searching in a promising patch, then maybe back to broad exploration if the patch dries up.
Or in optimization, maybe resetting hyperparameters versus just resetting the starting point within a given set of hyperparameters.
Could be, yeah. Different levels of intervention. The potential impact is significant for really large, structured problems. It could stop agents getting bogged down for ages in one small, unproductive part of the overall space.
These are really thought-provoking extensions, building directly on what the paper achieved, but pushing it further.
Definitely. And, just to be clear, these are just speculative ideas, food for thought.
Of course, standard disclaimer applies.
Yeah.
But they show the richness of the original research.
Absolutely. The core paper really does lay a strong foundation. It significantly pushes our understanding of how RL can optimize search using resets.
It really highlights ML not just as an engineering tool, but as a tool for scientific discovery, too, finding new principles.
Couldn't agree more. It's helping us understand fundamental processes in a new way.
Well, we definitely encourage you, our listeners, to check out the original paper. We'll put a link in the description, as always. It's worth digging into the technical details.
For sure.
And maybe as a final thought to leave you with, how could these ideas about strategic resetting, about knowing when to stick with something versus when to cut your losses and try a fresh approach, how might those principles apply in your own field, or even just problems you think about day to day? Something to ponder.
Good question.
Thanks for taking this deep dive with us today.
My pleasure.